Hello and welcome to this video. In this video, I'll be talking about network address translation. Network address translation is one of the good and bad technologies in the development of the entire networking internet. Good because it has helped us to keep using our IPv4 addresses even close to the exhaustion, and bad because it is somehow preventing us from enjoying the benefits of the next gen IPv6 address or IPv6 addressing. So I'll be talking about network address translation, the motivation behind it, the implementations, what it means, differentiating private addresses from public addresses. So let's get right into network address translation. So with the development of internet and the increase of network applications, the limited public IPv4 addresses have become the bottleneck of network development. In order to solve this problem, network address translation was introduced. Network address translation enables hosts on an internal network to access an external network. What are these two? We'll look at that. It not only helps alleviate IPv4 address shortage, but also improves the security of the internal network because NAT prevents devices on the external network from directly communicating with hosts on the internal network that use the private addresses. This chapter describes the motivation behind NAT, the implementations and application scenarios of the different types of NAT. In order to cover these descriptions, we've set up our three objectives of this chapter. First of all, you'll understand the motivation behind NAT. Why was it introduced? What is the main motivation? Which problem is it there to solve? Secondly, you'll master NAT classifications, which is also really its implementations. Finally, you'll master NAT selection in different scenarios. Which NAT implementation should we use in which scenario? So in order to achieve these three objectives, we are going to break up the chapter into an overview, then static NAT, dynamic NAT, NAPT, and easy IP, and finally we'll look at NAT server. Let us start with the overview, and first of all, write with motivation behind NAT. So we know that the number of internet users increases exponentially on a daily basis, in fact hourly basis, if not second basis. The public IPv4 addresses, which are the addresses we use over the internet, become scarcer every day. And what's worse, there is uneven allocation of these public IPv4 addresses, and that has resulted in severe shortage of the IPv4 addresses in some areas. Actually, there are areas which no longer have IPv4 addresses at all, while others have extremely few that are right now with the hands of internet service providers. In order to overcome the public IPv4 address shortage, it is necessary to use what we call transition technologies. What this means is that we have used IPv4 and have designed a lot of networks, service provider networks and huge enterprise networks, all based on IPv4. And here we are moving up to IPv6. But we can't exactly change everything we have been using to support IPv6. There are protocols that are IPv4 protocols. There are technologies. There are several implementations and services on our networks that are just based on IPv4. We can't just jump all over to IPv6 because it's better than IPv4 because it has more addresses than IPv4. It's not possible. So we develop transition technologies that help us to run IPv4 together with IPv6 in the process of transition. One of these technologies is NAT, and there are other tunneling technologies, but not in the scope of this chapter. So as you can see here, the number of internet users increases exponentially, while at the same time, the number of IP addresses they need to use is decreasing exponentially. At some point, the number of IP addresses drops to 0 while the number of internet users continues to increase. Well, because of this challenge, at some point, the developers of the internet thought of dividing the entire IPv4 address space into two major parts. So the IPv4 address space starts from 0.0.0.0 all the way to 255.255.255.255. That gives a total of 4 billion addresses, 294 million and something, some big number. It's 4 billion addresses precisely. Now, we divide this entire block of IPv4 addresses into two. Now, I hope we do not confuse this with classes of IP addresses. Because when you talk about classes, class A and class B and class C and class D, A, B, C, D, and E, mainly of which we use A, B, and C for unicast networks, which we look at mostly in this course. So when you look at our classes A, B, and C, these classes were, again, this entire family of IPv4 addresses gets split up into two major types of addresses. IPv4 addresses get split up into what we call public addresses and private addresses. So, the public addresses are the ones that are going to be routed over the internet. If you want to speak to anyone on the internet, you need to speak to that person's public IP address, and you need to speak to them using your own public IP address. Your private IP address is private to the network where you reside. It cannot be routed over the internet. Now, why is this important? Well, it's important because now private IP addresses can be used repetitively by different organizations since they never crossed the boundaries of the organization. So let's say this right here is Stanbic Bank, and this right here is Makerere University, and this right here is URA. So Stanbic Bank is going to have private IP addresses. Let us say 10.0.0.0/8. Makerere University will have the same IP addresses, 10.0.0.0/8, and another enterprise will have the same addresses, 10.0.0.0/8. These are private addresses. The idea is that any host inside this enterprise cannot communicate with one of those addresses because those addresses will not be allowed outside of this boundary. The same applies to that. These can't be allowed outside that boundary, and these cannot be allowed outside that boundary. They can only be used inside their internal network. In the internal network, that's where those addresses are going to be used. So now the question becomes, what happens if Stanbic Bank staff want to communicate outside? What happens if Makerere University students want to communicate to Facebook, to Google? Well, we're going to deploy network address translation somewhere here that's going to change this private address into a public address that can be allowed on the internet. When it reaches the destination end, a reverse kind of implication, a reverse kind of happening the reverse of this will happen on the receiving end. The public IP address will be converted into a private IP address, and so we communicate internally to that network. So what are public addresses? Public addresses are addresses that are managed and allocated by a dedicated organization and can be used for direct communication over the internet. Private IP addresses, on the other hand, can be used by organizations or individuals randomly on their own internal networks. They cannot be used for direct communication on the internet. Well, I think technically they actually can be used, but it's a requirement on internet service providers to block all those private IP addresses referred to as 1918 addresses. They are blocked on the routers of the internet service provider. So even if you try to communicate with the private IP address, it's going to be blocked by the internet service provider. So it will actually never ever get to reach the internet. Now, of our classes that we already talked about in chapter 3 of this course, network layer protocols and IP addressing, we talked about class A, B, and C as the classes of IP addresses used on unicast unicast communication, we have a fraction of each of those classes reserved as private IP addresses. For example, in class A, we have the addresses from 10.0.0.0 up to 10.255.255.255 as a private network. These can only be used in the private. Remember, class A starts all the way from 1 up to 126, but the 10 range, 10/8, is all reserved for private addresses. In class B, you can see that 172.16.0.0 all the way up to 172.31.255.255, these are reserved as private addresses. They cannot be routed over the internet. In class C, 192.168.0.0 all the way to 192.168.255.255 are reserved as private IP addresses, and they cannot be routed over the internet. Now, you will recall that a class A address will have up to 16 million IP. A class A network will have up to 16 million IP addresses. A class B network will have up to 65,000 IP addresses. A class C network will have up to 256 54 actually, IP addresses, if you remove the network address and the broadcast address. Now, these classes are going to be used by organizations based on their size. So you might be wondering, why should we have a class A? Why should we? So a big university like Makerere University, like Harvard University, is typically going to choose a class A network. A big university like Cambridge is typically going to use a class A network. So they will all keep using this class A network, 10.0.0.0 and 10.255.255. They will subnet it and use it internally for their communication. Now, for every instance where they need to communicate to the outside world, they are going to put somewhere along the boundary at the egress device. They are going to set up NAT, network address translation, that can translate the IP addresses in this network into the IP addresses allowed on the public internet, and the communication will happen. The translation of the source address from a private internal address to a public IP address that will communicate over the internet is exactly what network address translation is. So, in this illustration, we have enterprise offline campus, we have small-scale factory park, we have school campus network, we have a home network, we have coffee shop. You can look at all these are using IP address networks, IP networks in the ranges of private networks. However, around here, outside each of them, if they need to communicate to each other, they are going to send packets that are going to traverse the internet. Those packets moving around the internet cannot be moving with the source and destination IP as private IP to private IP. It's not possible. What that means is that somewhere at the boundary, we are going to deploy this guy called NAT. What NAT is going to be doing is to convert this private IP address to a public address that's going to be used over the internet. The NAT right here will convert the public address back to the private address. When this guy responds, NAT will convert the private source address to a public source address somewhere there and send that packet with a public source and destination IP address. When it reaches the other end, the reverse of that will happen. This is what NAT does, ladies and gentlemen. So, how exactly is this going to be implemented? As I've mentioned, it translates IP addresses in the IP data packet. So it gets hold of the IP header. We looked at this. It gets hold of the IP header and it swaps the source IP mainly, as we shall see. Well, in some cases, it actually is swapping the destination IP, but it will swap the IP address from private to public. That's the idea, and maybe public to private when it reaches the destination end or when it receives a reply. So it is widely used on live networks and is usually deployed on network egress devices like routers or firewalls and typical NAT application scenarios. is where private addresses are used on private networks, that is mainly enterprises and homes, and NAT is deployed on the egress device that connects our private network to a public network. Now, for traffic for an internal network to an external network, NAT is going to translate the source address, as I've mentioned. If traffic is coming from our internal network, this network, going out to the public network, NAT is going to change the source IP, which is a private IP, it's going to change it to a public IP as the source IP, because that IP is allowed over the internet. And for traffic that is coming back from the public network into the private network, if traffic returns from the public network into the private network, what NAT is going to be doing is to convert the destination public IP, as indicated here, to a destination or private destination IP, thereby sending the traffic back to the original host that sent out the original traffic. This is basically what NAT does. So when we get hold of NAT and use it together with private address space, we effectively conserve IPv4 address spaces. But how exactly does this happen? We are going to look at the different implementations of NAT to see how exactly it happens. But the idea is, now we have addresses that can be used in almost all private networks and a few addresses that are used to exchange the packets over the internet. So if a host that uses, again, a private IP address needs to access the internet, NAT must be configured on the network egress device, in this case, this NAT device here, which is a router, to translate the private source address in the IP data packet header into a public source address. So generally, that is what NAT does. So we are going to talk about the different implementations of NAT depending on the scenarios. There are 4 basic implementations of NAT that we shall be talking about. The first one is what we call static NAT. So what is static NAT? That's going to be the first implementation of NAT we are interested in. The second implementation of NAT we are interested in is what we call dynamic NAT. Dynamic NAT. The third one we are interested in is PAT, or port address translation, also called NAPT, network address port translation. And the fourth one we are interested in is the one we call NAT server. So these are the 4 different implementations of NAT that you should look out for and be very comfortable with their implementation, how it works out, and how it can be configured. They are really, really important for your coverage of this course and for understanding of actual world, of actual network applications of NAT. So this has been the NAT overview. In the next video, I'll be covering static NAT. I hope this has been informative for you, and thank you for viewing.